AI-driven chip design is a thing now. What excites me the most is that AI research, be it within EDA or outside of EDA, it's still outpacing Moore's law.
From EE Tech Media, this is Moore's Lobby, where engineers gather to talk all about circuits. I'm your host, Daniel Bogdanoff. Today, it would be a crazy and probably impossible task to design a chip without a powerful computer and a big old tool chain. Today, we're going to explore a bit of chip history, chipstery, if you will, and the future of chip design from the perspective of someone who spent decades building parts of that big old tool chain. In the lobby today, we have Stelios Diamantidis, a distinguished architect and head of AI vertical strategy at Synopsys. Synopsys is the #1 global leader in silicon design and verification, so I'm very excited for this. Stelios, thanks for being here.
Oh, thanks for having me. I'm very excited to be here as well.
What first got you excited about technology and electrical engineering?
You know, in everyone's life, I think there were maybe 1 or 2 or 3 aha moments. For me, maybe that was one of them. I'm part of a generation that didn't really grow up with computers. I look at my own kids these days, and quite honestly, nothing can impress them anymore. But for me, it was a lot easier. I still remember the day that I actually saw my first computer. I was in school. I believe I was in junior high, maybe middle school. One of our teachers there, in fact, I believe he was a math teacher. We didn't have a computer science class. It wasn't a thing at the time. Just said, "Hey, I got something really special. If you want to come join my class after hours, after the end of the school day, I can show it to you, and it's going to change your life." And of course, you know, I think everybody went to check out what was going on. I don't think we expected to see what we saw. What we saw was really, to me, the very first computer I had ever seen, maybe other than in movies or science fiction. And it was a very modest experience from that point of view. It was I believe a Spectrum ZX featuring a whopping 32 kilobytes of memory at the time. So nothing to really impress anyone these days, but at the time, just looking at the machine and then the things that it could do, which at the time were mostly, you know, some number crunching, maybe some very simple spreadsheet kind of applications and really impressive games. I think it was one of those moments for me. I knew I was hooked, love at first sight kind of thing right then. And then, you know, as my overall academic and then professional careers evolved, there were more moments that sort of reassured me that was the path for me. That's how it started.
What was your first personal computer?
I had, and you know, I did grow up in Europe, so this may not actually click with a lot of people, but there were a manufacturer in Europe called Amstrad Computers. And Amstrad, they were UK based, and they made models. I believe there was the 464 and the 528 or something to that effect. It was basically a function of how much memory they had, and they came equipped with a cassette player. And what was really groundbreaking at the time, it was the only computer that came with a monitor, and it was a color monitor. I think it had 64 colors. I still remember that machine, and quite honestly, to this day, I am just floored just thinking what people could actually do with those modern resources. One of the things that you could actually do with those kinds of machines that became very popular with folks like me is that they came with basic preloaded. So you basically turn it on, it booted, and right there, without any additional software or opening editors or whatever, you could start actually writing programs right off the prompt. And they became very popular with sort of like the geeky squad about what the kinds of things you could do with them. So we're looking out to the, there was a magazine that came out every Friday called RAM, and you could post actually solutions to problems and share code on the magazine. So, you know, I'd be looking, I'd be in line, pick up a magazine, typing, "Oh, this is awesome, share mine," let it to the editor. It's really fun times.
Was it called Random Access Magazine? Because if not, that's a missed opportunity.
I think it was as RAM. I don't even know if they knew what RAM meant, but it was a cool name.
So then you got an electrical engineering degree. Where did you go to school for that, and what did you study?
I actually, I grew up in Greece, and it was a great place to grow up. not a technology hub, but gave me so much opportunity to be able to look around and then and look at the things that I could potentially do with my life. And I ended up actually going to university in the UK, and that was a great experience on its own. It was more related to being able to get a global experience, a world experience with life, and it certainly did deliver that. So I went to the University of Kent. In the UK, I got my bachelor's of engineering in computer systems engineering.
Did you then get your master's degree right after that?
I did. In fact, it sort of came naturally. I was actually thinking it'd be a great opportunity to maybe start doing some work and get some work experience. I had done some internships during the summers. I had gotten some exposure. But then the opportunity came along to cross the pond, as they like to say it, and come study in the United States. And so it became my new chapter very, very quickly. I was fortunate enough to get a position at Stanford. I came to California. In fact, I have a story about that too. I was pretty good in school, so I was given the opportunity to do a postgraduate degree at Stanford in California. At the same time, I also got accepted into MIT. And I remember, I had spent 4 years in the UK, right? So I really didn't know very much about the US at all, I have to admit. And these were the very early days of the internet. We had Mosaic, and you had to wait for a few minutes for a page to load. But both universities had a web page. So I loaded both of them and I put them side by side. And then I realized MIT gets a lot of snow. And right there, the decision was made. The other picture had palm trees on it.
Yeah. Greece,
Yeah.
I suppose, is not known for snow.
No, it's sort of like I said, that's enough time in the cold. So that had a lot to do with it. But well, it was basically a no-brainer kind of choice. Both options were equally awesome.
Wonderful. Yeah, that's quite the decision to be able to make between MIT and Stanford.
No, yeah, you can't even ask anyone either because they're not going to be very sympathetic, right? So it was kind of a funny
Yeah.
time. But yeah, it was just great, a great opportunity to really come to the epicenter of it all. And I'm not referring to the fault line here, but the epicenter of technology, and really get exposed to it firsthand. It was incredible.
And what did you do your graduate work on?
I actually did it on networked systems and distributed systems. So it was a combination of networking, which was, we're talking now mid 90s. So networking was super hot. Cisco and other companies that create the backbone of the internet were very strong at the time. But at the same time, distributed systems, and specifically distributed operating systems, were very, very interesting to me. So I did a lot of coursework and some project work on those. And then in addition, both in the UK as well as when I arrived here, I was fascinated by neural networks. So a good proportion of both my undergraduate degree and my graduate degree, I looked into neural networks as a technology. And that really, I think, ended up impacting my career down the road as well.
What was it like studying neural networks and AI systems in the 90s? I think there was so much groundwork laid then.
Yeah.
But it wasn't really considered to be, I don't know, viable or a modern topic at that point, I guess.
Yeah, it was, in academia, you had pockets where the research continued, and it was actually very interesting. Most of the academic work I was exposed to was around image processing. And they were, an overall part of parallel computing. So you could actually get quite a bit of coursework on it. The thing is that everybody admitted at the time that while this was really cool, and it had been around for some time, right? The whole neural network body of research and the math behind it started in the 40s. So even though that was really something interesting, and artificial intelligence had captured the imagination of people, both in academia as well as folks in the arts, in literature, film, it had failed to really capture the market. So the real life applications of AI just hadn't happened, so that it became something mainstream, something that everybody got to touch and interact with. And so it was a little disappointing when I started talking to employers, and it was very clear that passion was going to stay a passion, And at the time that we were going through our what officially is known as the second winter of AI, and it was exactly that.
You mentioned graphics. Can you tell me about your first job out of school?
So that was another dream. So during my stay at the University of Kent, I really enjoyed working with workstations. We had a really nice line of at the time I think it was Hewlett Packard, the Apollo workstations, and then of course Silicon Graphics. Silicon Graphics was, we had a few of them. Everybody wanted to use those. The technology, unbelievable. The company, unbelievable. So when I came to the US, I had a very, very soft spot about SGI, and at the time they were really flying high. They were the technology company. If you allow me a parallel, the Google of the mid 90s was SGI. That's when Jurassic Park, the movie, came out. I remember Bill Clinton delivering the tech program for his administration at SGI, broadcasted all over the United States. And so all the cool things were happening around that company, and my dream came true. I was able to get a job with SGI, doing what I love, writing code. So it was just an incredible experience to be able to do that.
For people who aren't familiar with SGI, and you mentioned some standout moments, what did you do there, and what was the company known for?
The SGI stands for Silicon Graphics Incorporated. Graphics was in the name, and Silicon was in the name. So where they really, I think, broke new ground was that they were able to sort of accelerate the development of graphics computers. They were able to put a lot of the graphics algorithms, graphics processing algorithms, efficiently onto silicon. And then they were able to scale those systems up to the tune of not only multiple machines in multiple racks, but multiple floors of buildings, which was what was required at the time to deliver the processing power needed to do things like nuclear simulations or simulators for pilots that ran at near photorealistic resolution. Comparing to where we are today, you can do that with your iPhone now, which says something about technology. But at the time, this was the stuff of science fiction. And I was actually part of the advanced graphics group at Silicon Graphics, and I worked on some of those machines that delivered the unprecedented compute power that you find today in GPUs.
Taking things from massive scales to kind of small scale cell phone technology leads into my next question. What did you do after Silicon Graphics, and how did circuit design and emulation and bringing that to silicon play into your next role?
That's a great question. So Silicon Graphics, the folks at Silicon Graphics were some of the most remarkable folks I've ever met in my career. And I think every single one of them went on to create other companies and other innovations that to this day we're experiencing. So it was a sort of like a third university for me, quite honestly. And some of the things that really caught my attention, which really wasn't part of my original direction of looking into networks, but I became enamored with building chips. I found the miniaturization of algorithms and the process of capturing them into silicon just fascinating. And along with it, of course, came the challenge. And I think maybe that was the part that mostly resonated with me. How on earth are we getting those things to work? And at the time, I was looking at 250 nanometers, right? And so 250 nanometers for me was unfathomable. I was like, we can't do that. So my work at Silicon Graphics started being more and more in the domain of designing and verifying chips. And I saw an opportunity to take some of these learnings and some of the experiences and really see if we can actually bring them into the market at scale and make that technology work for everyone. And that really is what sort of took me to the next step in my career, which was to go out and start my own company in what I guess you would call today EDA. Maybe it wasn't quite EDA at the time when we got started. But I found that the process of building and validating silicon had so much promise that I decided to do my next venture in that area.
So you started your own company, jumped into a founder and CEO role. I want to hear more about that, but it's time for a quick break. We'll be right back after a word from Microchip, this episode's sponsor. Are you looking to design reliable technologies that make a difference in various industries? Microchip is the global leader in microcontrollers and analog semiconductors. Microchip provides smart, connected, and secure solutions that empower innovation to enhance your designs. Their focus on security and connectivity sets Microchip apart, ensuring that your designs are always up to date and protected against potential threats. With their microcontrollers and advanced analog semiconductors, you'll be able to bring your ideas to life. Learn more at microchip.com. Start designing with Microchip today. We're back with Stelios Diamantidis, Distinguished Architect and Head of AI Vertical Strategy at Synopsys. So, Stelios, you started a new company after Silicon Graphics. It sounds like you kind of jumped right in at the deep end.
I really did. And quite honestly, I had no idea what I was getting myself into, which became kind of like story of my life. The idea was that we could actually build platforms that could bring some autonomy to the verification problem. So, at the time when we got started, engineers would study a spec, and then they would write tests for that spec, and then analyze the results and determine whether the design that they were verifying was actually functionally correct. It's a excellent way of doing things because it's very accurate, and the designer experience is not something that you can replace. However, it doesn't scale very well. You need designers to scale it, and then at some point, you just can't get enough people to work on the problem because the chips are getting bigger and bigger and bigger. So the idea was, can we get a machine to do some of this? And if so, how can we leverage the designer expertise to create the questions and then have the machine start answering the questions, really what it was? So interestingly enough, once we got going with my company, we discovered that there were also other companies that were looking at other aspects of this problem. So we ended up partnering with some of those companies to build high-level solutions. One of those companies that I, really dear to my heart that we work closely with were Veracity Design, originally out of Israel. And their technology was really cool. We were really complementary in vision, so we partnered together, and we brought, I felt, a lot of great solutions that were used by many different companies to tape out designs throughout the 2001, 2006 timeframe.
Yeah, I remember at one point bringing up Carnot maps to a chip designer, and they just chuckled like, "Oh yeah, we don't use those anymore," because the scale of the problems gets so large so fast that manual checking and test writing is not nearly enough.
It is not. The idea at the time, and which is still to this day the predominant methodology for verification, for RTL verification, is that you can capture constraints around the behavior of a system, and then you can let a machine essentially randomly traverse the problem space, looking for problems, not intentionally, but at very high scale, right, which solve that aspect of the problem. And then develop metrics around the process of driving this verification. And it really allowed people to do a lot more than what they were able to do at the time, meaning the early 2000s and earlier. And it was a breakthrough in productivity. And then it also gave birth subsequently to IEEE standards like System Verilog that allowed everybody to capture this kind of methodology into all the different products that we use today across EDA. So it was really a fantastic breakthrough. What we ended up doing with my company, we ended up really focusing on individual protocols and individual subsystems, and really working on so who's going to capture those constraints? That was still a manually labor-intensive engineering problem. We worked on that side of the problem using commercial platforms that then the big EDA companies, the Synopsys and the Cadences, by the time had commercialized.
So how did you decide to start a second startup?
Well, I love the analogy of plateaus, right? Whenever you're part of an activity, you reach plateaus, and then that gives you vantage points into other areas, some of them that you hadn't actually considered. And that's how I originally got involved in verification. The second startup really was, I think, a confluence of two things. The verification space experienced some consolidation right around 2006 or so, that kind of time frame. And it was a good opportunity for us to rethink, go forward, rethink the strategy, have an exit. And then the second startup was really about, the problem of validation extends beyond virtual models. In fact, it's a very real world problem. I remember talking to companies like Cisco at the time. They had this very, very complex enterprise switching systems, many ASICs on highly complex boards that they couldn't quite debug because they didn't have the visibility into those systems when those systems were running at speed to understand exactly what was going wrong at any given time. So they had what they call a dog pile of boards that they couldn't actually debug because of that lack of visibility. So it's not a question of hooking up equipment to observe. You just can't actually do that. It's deeply embedded in the chip. So how do you look into the guts of the chip while the chip is in operation and be able to understand what is going on? And quite honestly, that question to this day is not fully answered. We're doing much better, clearly. But now I guess the time frame is the late 2000s. The answers were very, very sketchy at the time. So what the second startup ended up being about that we did, test ESL automation, or Tesla, prophetically, was really about how do we instrument a chip to be able to observe some of the effects that would lead us to debugging the chip itself, and then how do we leverage all the design information that went into making this chip so that it can guide us through the process of understanding what's wrong with the chip is not properly functioning at speed, even though it's passing all of our other tests on the tester or structural tests or manufacturing tests. Awesome space. And I think now, if I look at the industry over the last couple of years, I'm really looking at companies that are actually going after this very, very aggressively in the space that we call SLM, or Silicon Lifecycle Management. One of them is Synopsys. I'm very excited about what we're doing in this space and what my colleagues are now working on to make this Silicon Lifecycle Management process and problem space a place of enablement, a place where we can actually harness the data and use it to extend the lifetime of the products, make it easier to anticipate failures, make it easier to anticipate maintenance events if they need to happen. All kinds of incredible applications that also bring us into the whole big data analytics domain that is very, very hot as well. So really cool stuff. But then 2009 happened, and it wasn't very kind to a lot of folks, and we were no exception.
Yeah, I don't think too many people look fondly on those couple of years from a professional standpoint. Can you walk me through Silicon Lifecycle Management?
Yeah, absolutely. And there are many aspects of it. So maybe I'll just cover a few. But generally, we build these giant chips in this very forward-looking technologies these days, right? Tons of logic. In fact, so much logic that we can't even power all of it all at the same time. But incredible features in those chips, right? Somehow we've been able to keep it going to 5 nanometers and even below, where we're using just unfathomable kinds of tricks to get the actual wafers printed to begin with. But we can do it, and we can make them work, and we can make them work at incredible speeds, and then we deploy them, right? And then think of the deployment environment. Some of these chips go into data centers where you have an expectation that you're going to have this, pristine voltage, pristine temperature, always within very, very low error bars, and the chip is expecting that. And then some of them are going to go out in environments where you have absolutely no idea what the temperature is going to be like, the noise levels are going to be like. The deployment environment is largely unknown. And then some of those chips are even going into environments where they're expected to perform safety critical functions and mission critical functions, right? I'm talking about vehicles, for example. So again, we've done an incredible job as an industry to put those chips in those sockets, and they work great. But we can't anticipate what we can't anticipate, right? And the question then becomes, can we continue to sort of maintain a sort of observability chain, not only from design to manufacturing, but from manufacturing to deployment, so that we can understand if anything, for example, may be going wrong with this chip, even though it's so complex, and even though it's remote and in an unknown environment. And that is one aspect of Silicon Lifecycle Management that I find very, very interesting, right? How do we do it? Well, one good way of doing it is to, first of all, insert into the chip instruments. And instruments are small pieces of circuit themselves that do not impact the operation of the chip, but allow us to essentially have a sort of a biometric data flow coming out of the chip that's telling us that everything is doing great, or if some events that have not been planned for are actually happening. And this could be that the power delivery network is essentially experiencing spikes, for example. It could be something that has to do with clock, which navigates everything and controls everything. It could be with being able to identify even some logic errors that are unexpected, pointing to maybe some sort of degradation in the silicon that's leading to functional errors. Really, sky's the limit as long as you are very careful not to impact the way that the chip operates. And at the same time, of course, make sure that all this monitor logic and instrumentation logic doesn't take away from the ability of the chip to be competitive. So it cannot take up too much area. It cannot require too much power. You need to have somewhere to place at least a scratch pad where you can place things that are happening before you can ship them, right? You don't take too much energy shipping the data to whoever needs to know. All those kinds of things. It's a fascinating engineering problem all around. And what you get on the other side is the ability to essentially actively manage not only the specific chip you're monitoring, but a family, if you'd like, a whole group of chips that may be in similar environments, maybe in the same environment, maybe in different environments. Figure out how to manage your behavior of products as a fleet, for example, if you're a transportation company. Schedule predictive maintenance. If you're seeing, again, across your fleet certain behaviors that are pointing in the direction of some systemic failures, schedule maintenance. Replace parts before they fail. Even if one of them was to cause some sort of accident, preventing that is immeasurable return on investment, right? So give the operators the ability to make decisions based on the behavior of the chips is a huge gain. And then there's so many others that you could think of. Security is a huge one, for example. We live in an environment where security chains need to be guaranteed, and hardware is not an exception. So that's a really great one. And the list goes on and on. It's a fascinating area.
So what I'm hearing is there are a lot of inputs and a lot of potential outputs, which sounds like a perfect role for AI and machine learning.
Yeah, that's right. That's correct. Yeah.
And that aligns really well with what you're doing at Synopsys. What gets you excited about Synopsys, and what are you working on there?
Yeah, so Synopsys, I've always worked with Synopsys, right? So Synopsys is really, and this is no exaggeration, Synopsys technology is part of every single silicon design project anywhere in the world. And that on its own, I think, is remarkable. What really fascinated me with Synopsys is the opportunity, meaning there are so many things that they have done, incredible management, incredible leadership in, starting with our CEO, Arta Jus, and then the technology foundation that Synopsys has in tools, in algorithms, in engines, in IP, in customer collaborations, really makes an entrepreneurial guy and a founder guy like me thinking, man, that is just a huge playground. And the kinds of cool things that we could be doing within a company like Synopsys could be really, really cool. So that really is what really attracted me to and of course I knew Synopsys very well and the folks there, and I had, as I said, a lot of respect for the folks that worked there, and that's what started the conversation. And when I started at Synopsys, no surprise, I was already in the sort of instrumentation, design for manufacturability, design for yield world. So I joined and I took on a role looking at the technology behind their DFM, design for manufacturability products. Sort of really the interface between where the design world ends and when the manufacturing world sort of begins. And it was a great ride. We had a really great new product at the time called IC Validator, which was essentially a flexible framework that allowed you to program all kinds of applications that you would ultimately run on data sets that go to foundries and get manufactured, to ensure that you have proper spacing relationships in shapes, to ensure that you have your forced manufacturing rules, perform certain steps to improve manufacturability and yield silicon, and then even to match patterns that are in a statistical manner impactful to manufacturing, which was one of the key technologies that I worked on during my early days. So it was really a lot of fun, starting a new journey and really getting to work on such a huge technology foundation.
So what are some things that chip designers miss when they, maybe it works functionally, but when they go to manufacturing, it becomes a challenge? Are there any geometries people get wrong or anything like that you noticed?
The interesting thing is not really what they miss, is what they don't know they miss. I mean, maybe is a better way to put it, right? So if you look at folks working on the forefront of new silicon technologies, they're designing stuff while at the same time the manufacturers are working with early versions of their processes. So certainly the advanced designers or designers working on next generation nodes, but then to extent all designers are sort of in this constant learning loop where they're trying things, where they're getting feedback from many sources, where something that you do may fix a problem, may impact another area. It's a multidimensional problem that I don't think it's any designer could possibly address in its whole. So you have to be flexible and you have to pivot and you have to think on your feet and solve problems quickly. And then over time, of course, the new process matures and it becomes easier and easier, clearly, to be able to create manufacturable designs. But then the other thing jumps in, which is, you're constantly pushing the envelope of performance, be it frequency or be it power or be it the sort of area that those designs actually take. So then you're competing with yourself and with what other folks can do with that same silicon process. So in other words, yes, your manufacturability maybe you have more answers than you did in early phases of design, but you have the constant pressure to optimize, to arrive at optimized solutions for problems that are intractable. It's a very, very difficult task for engineers. And that's why, going back to my comment earlier, I am constantly stand completely impressed at what people are able to do with the problems that they have to deal with in chip design. But they do it. And so a lot of respect for designers.
Now, I'm hoping you can help provide some context for this. Your title is Distinguished Architect. What does that mean and what do those duties entail?
Yeah, I think... so that's my title at Synopsys. Distinguished architects are folks that have demonstrated, of course, technical excellence. But at the same time, one of the key requirements is that this technical excellence covers or touches a lot of different disciplines. So we have folks at Synopsys in our Synopsys technical career ladder that are experts of their domain. And specifically, I think our designations for those are scientists. And then we have folks that are very good at sort of bringing together elements from different domains that are more, they're more generalists maybe from one point of view, but they can very quickly go deep on any given domain. And those are our architects. And really it takes both in an organization, I think, to drive technology. Architects are generally good at creating solutions. And then scientists, those kinds of folks are very good at optimizing the individual domain that's required to get the best out of the solution itself. So you need both.
Okay.
Now, there's the other answer, which is an incredibly inventive name that I have to create a human resources department with. but that's really is the distinction. And so for me, it's a great opportunity, and for folks like me who might be listening to your podcast here that like to bring together heterogeneous challenges and be looking sort of really sideways versus deep naturally, it is I think a really inviting career path.
And your career path has a lot of both chip design and AI. What is your take on the current state of AI and what does it mean for the future of chip design?
I think it's we've been watching a revolution, and I know that sounds kind of cheesy, but we've been watching it now for some time, so it really is one. And it didn't just happen in chip design. I think just look around you, and you can see what's going on, right? We see AI really coming in to do things that we never thought really just 2 or 3 years ago would be able to do. So for me, for my personal story, going back a few years, after I had done some work both in physical verification, physical implementation, which is one of the most complex problems in EDA. It's the process of taking a validated functional model and then really creating something that you're going to ship to a manufacturer. Right? You take the translation from, in other words, from something like Verilog, some high-level register transfer language, and go through synthesis and place a route, and ultimately have an optimized physical model that you can actually manufacture. I think there are tens, if not hundreds, of intractable problems in the chain of things that need to happen for you to get such a model. So it's a very fascinating space. And that really is where that story started. And I think there was maybe a moment of inspiration going back to, I don't know, a few years, maybe 2018 or so, where we were looking at what AI was doing. And I think at the time it was mostly around image recognition, or, is this a cat or is it a dog, and all that good stuff. But then one day we read on the news, and I remember being completely flabbergasted because I'm a big chess enthusiast, that, DeepMind came up with a way to have a machine essentially teach itself the game so well that basically there's no point playing the machine anymore. And I was like, wow, everybody said machines are getting good, but not that good, right? Because it makes you think, right? What makes a great chess player is not just memorizing moves and the responses to moves. It is what we call intuition, right? Strategy. How do you teach that? So for me, it was like huge. And then, of course, Go and on more complex games, larger state spaces. This happened around 2016, if I remember correctly, 2017. And so in just brainstorming, the question came up, heck, what if we were to one day be able to treat chip design as a game, quote unquote, a very complex game, right? Because if chess has a lot of dimensions, even one step of chip design has trillions more. And however, the principle of the question stands, right? So it became a challenge, and it became a research topic. Very, very grateful that Synopsys, I really have to credit our general manager at the time, Sassin Ghazi, who really saw this as a must-do for the company, and supported this research to go out and see if there's any foundation to the hypothesis that we could actually use AI to drive aspects of chip design. And that work was, led to some fascinating results that allows us today to talk about AI-driven chip design as a real thing. But it started out as a moment of inspiration, and then working with some really smart people with some great executive leadership to go out and answer the question and take some risk.
What was the response to people when you started going in that direction, and what were some of the first challenges you tackled?
It was the same. The response was the same as my response. Are you kidding me? It's very hard to convince someone that you can teach software to deliver abstract thinking and intuition. And quite honestly, we're not. Abstract thinking and intuition, I don't think are things that we even understand how exactly they work in humans. So we're not going to be able to teach machines how to do those things anytime soon. But we were able to get to the point that we can develop solutions that can make some limited decision making. And to me, if you think about machine learning as statistical methods to learn certain behaviors, and then artificial intelligence as a bracket of its own, what differentiates one from the other is not really quantitative, it's qualitative. Can a piece of software make a decision that I would otherwise rely on a human to make? And really that's where the point came that we were like, we can do a lot of things. We can teach the machines to do a lot of things, but at some point we have to accept that they can now make some limited decision making. So we're now in AI territory. So we developed our very first, I think, example of using this kind of technology, which later on came to be known as reinforcement learning. Reinforcement learning is the process of teaching a system how to make decisions based on the ability to learn from outcomes. So in a very simple way, you have an agent, you have a piece of software, just to be very colloquial, that can observe a system and then provide stimuli to the system. Based on the responses of the system, it can begin to try and learn some of the system's behavior. And by learning some of the system's behavior, it can begin to actually be intentional about what stimuli it provides into the system. In the world of chip design, our first proof of concept for this, I think, was playing around with clock construction for digital ICs. In clock construction, there are many different decisions that you make in terms of how to construct the clock, how to deliver the clock, and then ultimately different kinds of metrics that you're measuring to understand the quality of the clock. So the very first proof of concept that reinforcement learning can work in chip design came out of essentially giving a piece of software the ability to play with clock creation parameters, measure clock quality based on whatever parameters you try to tweak, and then over time optimize the outcome of the clock tree as an external, if you like, puppet master of sorts. And when we were able to do that, at least for me, for the first time, I was like, I don't see how this could not be applied to a whole gamut of similar problems. And I think that's also the moment where other folks who shared, the same sort of apprehension, if you'd like, or healthy even doubt about whether this kind of technology could apply, I think also saw that, there's potential here. There are things here that we're doing that we simply weren't able to do before with different kinds of technologies. And so it became, at that point, I think, we moved from a proof of concept to, okay, we're building a new enablement here for designers.
So where is that now? So you said the first proof of concept was, building out a clock tree.
Mm-hmm.
Where is that capability now, and where do you think that capability will be in 10 years or in 50 years?
Absolutely. So the whole direction of going from clock tree to the next level up led to the introduction of the first application for chip design using AI, which happened in March 2020, just in time for a global shutdown because of the pandemic. Great timing.
And a chip shortage.
And a chip shortage that ensued. And it was able to extend the principle of reinforcement learning for the entire physical design flow. So now, for the past 2.5 years, there's been this product out there that can plug into any physical design flow that runs synthesis and place and route, and help designers optimize that workflow by treating it as a reinforcement learning environment. It has been very successful in identifying solutions that generally engineers don't have the time or the bandwidth to do because of complexity and because of real life restrictions that at the end of the day they have to deliver a design within a certain time frame. So it has been very successful in augmenting designers' throughput.
What are a couple examples of situations that designers might not get to that are being solved by this?
There are many different ones. So in physical design, we generally classify the quality of output by the three-letter acronym: power, performance, area. Power, how much energy will this circuit consume to perform a certain task? Performance, how fast, meaning at what frequency can it operate? And of course, how much area is it going to take, which governs how expensive it's going to be to manufacturing, among other things. And some of these objectives are competing at any given time. So it becomes an optimization space, right? Now, when designers start working with any incoming design, what they bring themselves is the experience of having done it before, right? So when they're tackling a problem that is hugely complex, they tend to apply methodologies and solutions that have worked in the past. and that have allowed them to go meet those objectives. In any given physical design, you cannot a priori determine how fast you can actually make the part go, how much energy you can actually make it run with, simply because of the fact that, again, the complexity is leading to all these intractable calculations. There's no polynomial time solution for you to come up with a way of optimizing for these kinds of criteria all together at the same time. So it becomes essentially a search problem, right? It's as if you have this giant map and that you're gonna use to drive your car. You have to get somewhere, and you have certain constraints like how much gas you have, how much time you have to get there, and that is really what they have to do. But there's no GPS that's telling them go left here and go right there. So if they've done similar things before, they have something going for them. At the same time, that something becomes a sort of a constraint, right? They tend to be very, very hesitant about trying new things because, they know what got them there last time. And the time that it takes to even create a moderate complexity layout so that you can time it and you can determine whether you are on track, it can be days, and in some cases over a week of runtimes for you to be able to get a layout to measure. So it's a very, very tough problem to perform search under those conditions. So engineers have been very good at arriving at certain maxima or optima, if you'd like, but they can never answer the question, is this the global maximum or the global minimum that I'm looking for? Is there a better solution at the end of the day, potentially, that I could achieve? And this is unfortunately the complexity of the problem that's putting us in that position. Now, with this kind of technology, you can take your ability to run experiments and searches really to the next level, right? So where any given designer at any given time could maybe orchestrate 2 or 3 experiments to try 2 or 3 different aspects of the design and measure its goodness at any given time. With AI assistance, they can actually run tens of experiments at any given time. They're outsourcing a few of the decisions to the AI itself because at the end of the day, that's what gets you the automation you're looking for. But they get to set the global constraints. They get to tell the AI where to look, and more importantly, what to look for. And so now we're seeing the game of physical design, going back to the game analogy, being a game of you channeling your experience into constraints and goals rather than going through the tiny details of setting up experiments, running experiments, scraping data out of reporting structures, analyzing that data, deciding the next experiment, and so on and so forth.
Interesting. So it becomes a question of what are the key performance outputs and metrics, and less of a, how do I wire this up such that it runs properly?
It really is, absolutely. We have to handle the high volume, small problems with high automation so that we can let designers pour their expertise into the higher impact, higher value problems, really. And really, we shouldn't be surprised. If I look at the history of VBA, going back to maybe synthesis. Prior to synthesis, folks used to design hand-drawn circuits.
Yeah.
They were great circuits, right? But think about how many of those any given engineer could design at any given time or per unit time. Not that many. Synthesis came along, and a lot of folks were concerned that now if we make designers instead of designing circuits write RTL and then rely on a piece of software to generate the circuit, the quality is going to be gone, the competitors are going to be gone. We're removing the engineer from the loop. Nothing further from the truth was the answer, as synthesis enabled, I think, decades of innovation to happen because of the increased productivity. And then EDA has more examples. Place and route itself used to be much more manual. IP came along to sort of give us the ability to instantiate large blocks of logic that did things the way we expected because they were themselves designed by smart engineers. And I think we're seeing another leap here with AI giving us that great boost forward that enables us to build ultimately more chips and better chips.
Well, that's exciting stuff. I've seen some things around Synopsys and DSO.ai. Is that something that you're working on?
I am. DSO.ai is the acronym of Design Space Optimization. Design space exploration has been around for forever. It's a task that is not specific to semiconductors. Design space exploration happens in mechanical design, architecture, city planning, everything. Design space optimization brings together the aspect that we're not going to give you the ability to explore, we're going to give you the ability to optimize. So one level of enablement higher, maybe or two, above just exploration tools.
What gets you excited and what gets your users excited about this tool and the capabilities it brings?
Looking at now the last 2 to 3 years of working with customers on this, one thing that really excites me and that sets this technology gives it a special standing in my book is that we've been able to work with companies really across the spectrum of vertical markets and applications and even process nodes. And if you start thinking of the market, folks that are putting CPUs into data centers or are putting GPUs or accelerators into data scientists' hands, companies that are creating chips for vehicles and autonomous design levels, folks that are putting small IoT devices into wearables, or folks that are putting image sensors into smartphones or smart cameras, the list goes on and on and on. There are so many examples across so many different applications that have made this technology so universally applicable. And while everybody has their own definition of the problem, so the CPU guys really want the last megahertz possible, and the GPU guys are extremely sensitive about energy consumption. And then folks that are designing controllers for flash memory are very, very paranoid about size, because they're going to go and manufacture tens and or if not hundreds of millions of units of that stuff, right? Everybody have a very, very specific problem that they need to solve. And I'm extremely excited that this capability, this technology, has provided a framework for all of them, no exceptions so far, to actually come up with great solutions, right? No matter what the problem. So, we've had folks that we're looking to minimize leakage for parts that are going to be in an automotive environment because they don't want to drain the battery unnecessarily, right? And it's a very complex environment when you start thinking about leakage in digital circuits. It has to do a lot with whatever libraries you're going to use and how you're going to use them. And for them to be able to reduce leakage 15, 20, 25% in some cases was science fiction, really. It's quite remarkable, right? For folks like who are in very high volume businesses, to reduce cell area by 15%, over optimized designs, that is groundbreaking. This is differentiating in their industry. This is not an efficiency or a cost play. This is a competitiveness play. Folks that can change the floor plan of their accelerators to accommodate less or improve traffic, if you'd like, between processing elements for accelerators, which is a higher level problem, right? It's not strictly physical. It is really about how data flows through the architecture. And for them to be able to improve the way that the data flows so that they can essentially, well, you can see the benefit in many different ways, but maximize the way that they can process neural network frames with available hardware. Groundbreaking. The examples go on and on and on, because ultimately the AI is providing assistance. It's not telling these folks what to do, but it's giving them the ability to do what they need to do at the level of efficiency, productivity that just didn't have available before. And engineers are putting it to very good use.
So how should engineers think about chip design and AI, and where is all this going down the road?
AI-driven chip design is a thing now. With these kinds of applications like DSO.ai, we are able to address key aspects of chip design. What excites me the most is that AI research, be it within EDA or outside of EDA, it's still outpacing Moore's law. And the things that are really on a daily basis are coming out of academia, of industrial research, smart people everywhere sharing this kind of enablement, I have no doubt is going to lead to more and more and more powerful solutions for chip design, and ultimately make this process of creating chips, which has generally been a very difficult, very time consuming, very cumbersome task, something that's more accessible to folks that maybe have no background in chip design. They are trying to create some amazing application in a vertical that I've never heard of, and the ability to use AI to help them build the chip to get the product out there so that I can benefit and you can benefit and all that. For me, that really is what's so rewarding about this, and that's what I think the future of AI and chip design is going to take us.
Yeah, it'll be interesting when we get to a point where you can just define a chip's functionality. Say, here are my inputs and here are the outputs I need. And then to not have to know Verilog or VHDL and end up with a chip would be something else.
Incredible opportunity. Incredible.
In the last few minutes of every podcast, we like to do a lightning round, some fast, more off-the-cuff questions.
Okay.
One of my favorite ones, especially with your background, are there any situations in pop culture, books, movies, TV shows, that get AI really, really right or really, really wrong?
Oh boy, what a great question. I think I mean, going back to Isaac Asimov, for example, other great science fiction writers. Boy, I think they got so much right. It's actually almost scary how much they got right about AI. And what makes me really wonder is how much more they got right that we haven't seen yet, that I haven't thought of quite yet. Mm-hmm. So I really like the aspects of AI. It's sort of attractive to think of AI as sort of an indistinguishable robot that sort of has its own personality, then becomes sentient, and that may very well be. The future is unknown, right? But to think of AI, to think of the way that humans interact with AI, even in its most fundamental forms, even when it's very clear to you that no, it's not sentient and it's not a robot, and it's something you interact with over the internet, and what it tells you is based on things that it's read before. I knew ChatGPT was gonna come out of this conversation, and
Sure.
For sure, right? They can do that, but we know fully well what it is and why it is and what it does, and yet we fall in love with it.
Yeah.
So I think one thing that science fiction really got well is the humans' tendency to interact with technology and personify it naturally, even if, as I said, even if the wires are fully exposed.
That's a really good answer. Any advice for folks that are interested in getting into either the space of AI or the space of chip design?
For the space of AI, quite honestly, I don't think I have to say anything. I'm super excited that my kids in middle school know about AI, and they have ChatGPT accounts, and they're trying to interact with the technology, and of course by the time they become professionals, it's going to be completely different. But folks, I think, should continue to interact with AI and should continue to sort of learn and dream using AI. I'm not really subscribing to the group of folks that fear AI. I think just like with any other technology, the human race has the capacity to mess things up, but let's not think of our capacity to mess things up, but our capacity to innovate. And I think that's the future. Chip design, though, I do have a plea out there. It's no secret, right? The chip design space, specifically electrical engineering, enrollments have been down. The number of folks that enter the profession has gone down over the last, couple decades. Particularly in the United States now, there are official numbers that we're going to have a huge gap in the engineers needed to create the next generation of innovations with silicon. And so my message, if along your audience you have students, folks that are getting the profession, is get involved. There's a fascinating world in chip design. It might come across as intimidating to some early, but that's because you're looking from the outside in. persevere, double click, learn more. Reach out to, we have a great outreach program for the academia. Other companies have equally great programs to try and sort of bring young people and elevate awareness in chip design. And that's my message. It's a magical world to become part of.
Well, that is a great way to end it. Thank you so much for your time and wisdom.
Well, Daniel, thank you so much. It was a lot of fun talking to you. I appreciate you going down this the sort of the full rabbit hole with me. Lots of fun, and looking forward to chatting with you again.
Well, I love going down the tech rabbit hole. And if you are listening to this podcast, you probably do too. So thank you for sharing this time with me. That was Stelios Diamantidis, Distinguished Architect and Head of Strategy for Autonomous Design Solutions at Synopsys. If you like this episode, come visit us online. I'm talking about the Moore's Lobby social pages, and tag someone who you think will like this episode. And hey, if you're involved in chip design, leave a comment. We'd love to hear about it. And we're sending out some Moore's Lobby swag to folks who comment and tag other people. Also, make sure you're subscribed in your favorite podcast tool and on the All About Circuits YouTube channel. Thank you for joining me today in the lobby. It is a joy to get to do this with you. I'm your host, Daniel Bogdanoff, and I'll catch you next time.